Okay, hello together. Statistics and statistics can only be learned if we are doing exercises, and therefore we want to do today some exercises together. So first of all, we want to recapitulate the linear regression, and for this we look at some properties of the linear regression. So then let's take exercise number 1 and let's start. So first of all, remember linear regression was defined in the following way. We had y hat I is a plus b xi and y hat I minus yi is epsilon I, or we can also write yi is a plus bxi plus some error term epsilon I. So first of all, we want to show that the means of y and x are lying on the regression line. So that means 1 over n sum xi equals x bar and 1 over n sum yi y bar are on the regression line. Do you have an idea how we can show this? Well, we can just look in the first order conditions. And for this, I just look it up that I can show the first order conditions for you directly. This should be somewhere here. Up. Where we are, lectures. Statistics. And I think this was P9, I suppose. Nope. Then P10. Even P11. Here we are in business, I think. So here we have our first order conditions. And let's take them over here. Well, and then we obtain from this part here sum over yi minus sum over a plus sum over b xi equals 0. Then this we can both sides divide or multiply by 1 over n. So we have 1 over n, and thus we have y bar here. We have b times x bar here, and sum over a n times equals n times a. So this n and this n are cancelling out, and we obtain minus a. Oh, here we have also a minus sign, of course. Minus x bar minus a minus x bar, and thus we have x bar y bar equals a plus b x bar, and this is what we have over here. So this just means that the means of x and y are lying on the regression line. So thus y bar and x bar are on the regression line. So this is then A. What else? Oh, I have it here. Then, yeah, I think this I have shown already when we were constructing and when we were deriving A and B from the first order conditions. This follows from FOC, because in this lecture we have formally really done this calculation of the regression coefficients, and if you look it up, then oh, this has to be a x bar x squared. This is x bar times y bar. Or no, sorry. This we have when we calculating b. This is just inserting. This was still true. Okay. So this we have done. So we can go to C. The sum over all error terms has also to be 0 in the linear regression. This actually can also directly be seen from the first order conditions, and here the first order conditions. Take 1, and then we know that this is y hat by definition, if we look at this. So just inserting this means sum over y minus y hat equals 0. But the difference between the measured value and the theoretical value, y hat, and y is defined as the error. So this just means sum over ei from 1 to n equals 0. So what do we have also? The sum of the weighted errors, where the weights are the measured x values, are also 0. How can we show this? An idea? I think it is clear that it has to do something with the two first order conditions. So if we took for C the first order condition, then let's take for D the second order, the second first order conditions. Take, not fake, but take 2, and we will just insert. So then we have already shown from C that this part here is nothing else than the error. Just inserting this means sum over xi times epsilon I equals 0. So this condition is just the same as the first order condition, and this condition is just the second first order condition, only written in another way. So, and this you can keep in mind if you are doing a linear regression, then this means that all error terms have to sum up to 0, and all error terms weighted with the x values has also to be 0. And the last one, that you can write the sum of the squared distances from the y values with respect to the means, that this just splits into the square distance with respect to the theoretical values plus the square distance from the theoretical values with respect to the mean. And remember, this property we have used when we have interpreted our correlation coefficient where we have that this can be interpreted just as the percentage of the explained variance and the total variance, so that we really can interpret this as if r squared is 0.72, that we then can say that our linear regression explains 72% of the variance with respect to the mean of our values, because this here is nothing else than the total variance, and this by definition was then the explained variance. Remember this picture where we say when we have the mean, then this is the horizontal line, and if you then do the linear regression, then you just move your line, and then the distances of our data points will be a bit closer to this moved line than to our horizontal line, which represents just the mean of our data. So, and then we just start in order to show this. Let's do this just at another slide, because we need a bit more space. So if we take E, up, then we just start and we write out what we have here. So this is sum over yi minus y bar squared. And this, of course, we can write as sum over yi squared minus y bar times 2 we need sum over yi minus plus sum over y bar squared. Then let's take this term, more or less the same, yi minus y hat I squared equals, again, sum yi squared minus 2. And now we have in both variables the index I. So both variables has to be within the summation yi y hat I plus sum over y hat I squared. And the last one, sum yi hat minus y bar squared, we obtain sum over yi hat squared minus, and now here we do not have oops, hello. So I have learned that we have here our pointer who is calling our beamer that Sumber is inside, but he doesn't call that someone is inside. So hopefully it's come back. But I think you still hear me. And you see me also, because this is only a problem of the beamer, and therefore I can go on. So hopefully the picture will be back. There was no interruption for you, yeah? Okay, so the next time I can go on. So now here we have no index at the y bar, so we can also move this outside. This is a summation, so 2 y bar sum over yi hat plus sum over y bar squared. So, and now what we find here, then let's take them colors. First, here we have a plus. So then we see we have on the left side plus sum over y bar squared. In the other two parts, we find this only here. So this cancels out. Also, we find, let's take another color, sum over yi squared. We find only here. So this also cancels out. So what else? Then nothing else cancels out. So what else do we have? That we then are left with on the left side minus, oh, here, y hat, of course. Let's take it in blue. Y hat squared and y hat squared, but this is both on the right side, so we have together here 2 sum over yi hat squared. So in the end, we end up with this part here. So minus 2 y hat sum over yi equals the right side. There we have these 2 sum over yi hat squared minus 2 yi sum yi hat minus 2 y bar sum yi hat. So then the nice little thing is that all 2 are cancelling, and then we obtain yi hat, y bar, that these two are also canceling. No, sorry, do I haven't, where is it? This one, or here we also have a yi hat. So this and this. F1 is to this one is canceling. This we have. The reds are canceling, and 2 times y hat is also canceling. This is okay. And the yellow ones yi and is y bar. Okay. So then we take this on the left side. Then we obtain y bar times the sum over yi hat. So we do plus y bar sum over yi hat minus this one. So this comes from here and this comes from here. And on the left side, we find these two. These are still left. So this is yi hat squared minus yi hat. So this here is nothing else than our epsilon I. And this we can write as yi hat times yi hat minus yi. Again, this is epsilon, and this, by definition, is nothing else than A plus B xi. And so we obtain sum over A plus B xi times epsilon I. And this is nothing else than A times sum over epsilon I plus B times sum xi epsilon I. And now we are done, because we know that the sum over all errors is 0. So this is also 0, and this is this. And we know from D that the weighted sum of all errors weighted with x is also 0. And thus we have shown that we can really split the total variance in the explained and the unexplained variance. And this is a very fundamental result, because then we have a real good interpretation for the linear regression. So qualitatively, we have total variance equals unexplained variance plus explained variance. Well, and in most courses, we tell you only that this is the result, and you never have shown that this is the result. So again, that this lecture is about understanding statistics. So next question. Because of course, this lecture is also about doing statistics. Next one. A housing agent sells last April 26 flats with the following data regarding size G in square meters and rental M in euros. We know that the covariance is given by 5,760. Standard deviation is of the rental is given by 223.61 euros, and standard deviation of the size is given by 21.9 square meters, and the average rental is 1,100 euros, and the average size 80 square meters. So we want to calculate the regression line. So have I closed this? No, I don't have closed this. So these were the formulas which we have derived for our regression coefficients. So let's take, or we don't need everything. Therefore, we just take this one. So A, or question A, we have B is covariance over variance. So what do I have to calculate? Covariance is given by 5,760 divided by which number? Maybe you can help me. What is the variance given the data above? So then we have to say what is x and y, and of course we think that y should be the rental, and this is depending on the size of our flat. And we have this, and we have the standard deviation of the size, so 21.9 squared, because the variance of x is then, of course, the squared standard deviation. And if we calculate this, let's do this in Excel. So we have sigma g is 21.9, and we had covariance of m g, and this was 567. And then we have b equals 5760 over 21.9 squared. So roughly 12, let's say 12.01. So how can we calculate A from our data? Again, let's go into the formulas, and there we have this one. Copy. That we have, of course, equals y bar minus b times x bar. Well, of course, y bar is 1100 and x bar is 80. So we obtain 1100 minus 12.01 times 80, and this is then mu m was 1100 and mu g was 80. So we obtain A is 1100, equals minus, and I'm calculating exactly, times 80 is 139.22. 39.22. And why we are doing all this stuff, of course, we want to estimate something relevant from our direct data. We could say, well, roughly the rental of a flat size 80 square meters is roughly 1,100 euros. And now from our data, we want to make an estimation for a flat of 100 square meters. What do I do for this? Well, now we have A and B. A and B. And remember, our theoretical values, estimated values, are just A plus B xi. Yes, of course. So we obtain, how do I write it? Yeah, not y hat, but this is then m hat of 100 square meters is 139.22 plus 12.01 times 100 again. So step back. What is he doing now? And this is then roughly, or not roughly, I'm going to Excel again. M of 100 equals 139 plus B times 100. 1340.2. 1340.2 euros. So hopefully this is coming back now. Tip, tip. If I start it, yes, it's coming back. Okay. Next task. Again, some general questions. You know, this lecture is also about understanding. Within a random sample of 100 data points, we have found r square r equals, minus 0.93. And here are some questions, right or wrong. Since we have a negative sign in front of our correlation coefficient, we can say that there is, of course, no dependence between x and y. Right or wrong? And of course, please, with some statement, why do you mean this is right or this is wrong? So what is the meaning of the correlation coefficient? This we want to do in this exercise. Any idea? Wrong. If there was no dependence, R would be 0, of course. The negative sign of the correlation coefficient has nothing to do with the dependence or with the size of the dependence, so to speak, but this is only an, or I think this is asked in the next exercise, I think in 2 or 3. So we will not explain in this part A what is the meaning of the minus sign, but of course the meaning of the minus sign is of course not that there is no dependence, so this is wrong because no dependence, then of course R would be 0. The data points are scattering very near around the regression line. Of course, this is a qualitative statement, what means near, but I think you know what I mean by this. What do you think? We have our regression line, somewhere this one, or better this direction, and are now our data points far away from the regression line. Yes, of course. Very near, because we have minus 0.93, and we know that our regression, or that our correlation coefficient, is in the interval -1 to +1. And if we are very near at -1 or +1, then it means that that all our data points are almost on the line. So this is true, since R is very near at -1. And remember, R is element of -1 to 1. The linear regression has positive slope. Right or wrong? This is wrong. And why? So the answer wrong is true. And why is this statement wrong? Because R is negative. So this is the information of the negative sign in front of our correlation coefficient. If this is negative, then we know that, remember the exercise we have just done. The first estimation of our data points is, well, we look at the scattering about the mean. This is just the horizontal line. And then with our regression, we move this horizontal line maybe to the left or upward sloping to the right. And if we have to move it, and we go with the left side a bit higher, then this means that we have a negative correlation, that if we increase x, then we go down with y. Wrong, because R is negative, and therefore the regression line has to be negative slope. Well, and then the last one, right or wrong, the dependence. I already have answered this. I think between x and y is inversely proportional. Right or wrong? Inversely proportional means just if I go up with x, that I go down with r. So this is then, of course, true. This is only qualitatively formulated what we have in 3. So more or less only the other way around. This is the same question as in 3. Same question as in 3, only that we say y is going down if x is going up. Well, let's formulate another question, not right or wrong, but which, or here I can use this one, or this is better. Einfügen and text. Which proportion of the total variance is explained by the linear regression with an R equals minus 0.93. Let's say that this is 5. What do I have to do in order to answer this? So minus 93%. I think it's clear that this is not the answer. Hmm? So for this, we need the coefficient of determination. And this coefficient of determination was just defined as, let's see if I find this here. No. Then, oops, not here, but here, maybe 12. Yeah. This was R, and here we are. This one. Zip. Again, from the former exercise, we have explained variation and total variation, and this is just R squared. So we obtain minus 0.93 squared, and this is if R, oops, is, so this was, I think, number 2, and this is then exercise 3, minus 0.93, and then of course R squared is this squared, roughly 86.5%. No, there's only a minus. How much? 86.5. Okay, and then I think one is left. There we just do a linear regression, I think, or yes. So again, a brewery. I think I already had some example with breweries. So you'll see during nice summertime, I'm sitting outside having a beer. In 21, some brewery has the dependence between output and costs. So we have our 12 data points, and from these 12 data points, we should calculate the linear regression, and we should interpret the parameters economically, and we should also calculate the correlation coefficient, and in the end, estimate the total costs and average variable costs of an output of 1100 hectoliter. Okay, this we do also within some tables. So this were 2 and 3, and this is then 4. No. So of course, then we need x, we need y, and remember from our formulas, where is it? Here we need sum over xi squared, sum over the product of x and y, and we need the means of both variables, and here we need also the mean of both variables. Well, the easiest way to remember this is, I think, via this formula. But of course, in the exam, in the end of this lecture, you, of course, can use some sheet of paper where you have written down these formulas. Okay, so in this case, we need, well, I always used small letters because these are data points. So what did we need? X squared and xy. So x squared and xy. So, of course, oops, we want to have our cost function. This is what we want to do economically, and our costs are dependent on our output. This is how do you have done it in many lectures on business administrations. So this is just our cost function. So this should be y and this should be x, and we are interested into the cost function of our brewery. So what we want is c of x functional form. So then we take these data and hopefully I can just copy this like this. Let's see if this works. This I also want to show you. How do I get data out of some PDF files? So this works because this one I don't need. And this is not that nice, this form of the data. but this happens quite often if you are just copying data from some other files, from the PDF files. And for this, you just go, do you see this here? I don't think so. Oop. Sorry. Then this one has to be somewhere here. And I have to move the Excel file down. Let you see this. Maybe this is more important what I'm showing you now than the statistics, because you just go into data and then sort data. No, not sort. But this has to be larger. Where is it? Data tools, not filtering. Where is it? Here we have. Again. So now you should see it. Where do I have my picture? Because this I have to see now. That you see it also. So, data in columns. Up, there we are. Here we are. No, I have to mark it. And these are just separated with some spaces. Enter, and here we done. Nice little conversion of our data. Oh, this we have to move somewhere else. So this was output, and this was costs. So then we need the squared axis. So this squared, and we need the multiplied value, 600 times 6,500. And we need always the sums. Sum is sum. Sum. And I think I had 12 months, Oops. Equals this plus this. Oop. So from this we obtain the means. This divided by 12, and this has to be fixed with dollar signs. So these are our means. And then let's take this just that I can move it into PowerPoint. Up and up. Copy. Oh, not this. So, and with this, we can directly calculate A and B. So, B, this first, we just take again our formula here. I can cut it. This was this one. Copy. And thus we can insert X bar, Y bar. This is here. So this is 9, 6, 2, 7, 5, 8, 3 minus X bar times Y bar. So these two numbers multiplied 9, 9, 6. So here also times 9316 divided by X bar. So this is X bar, Y bar. This is X squared bar. So divided by 149,650 minus X bar squared. So we need this number also just squared. 9916 squared. So this, of course, I want also to do with an Excel. So I need then that B. Do you see this here? Oh, no, this is not good. Here we have to go. Now you see it. So this was then equals, open the bracket, this number minus X bar times Y bar, closing bracket, divided by, oops, this I have not in mind, so I have to look it up, X squared bar. This was the right direction. X squared bar is this number minus X bar squared. And hopefully I'm right. 5.86. Is this right? Yes. 5.865. So we obtain up equals 5.865. And A, of course, we again obtain here. We had it already. This was, where did we have it? This one. So this means Y bar 9316 minus minus B is 5.865 times X bar 991. So this means that A equals y bar minus b times x bar. 3531 or 308 if you also take 3 digits. 3500 308. Okay, so what else? Interpret these parameters economically. So this is A and B. What is the meaning of A? So actually, then we have our cost function. C of x is 3500 308 plus 5865 times x. Fixed cost, great. These are just fixed cost. And B are not variable costs. These are fixed costs, of course. And the variable cost is just the other part. So this you have to distinguish. These are the variable costs. Of course, the parameter B has something to do with the variable costs. But if you strictly interpret it, B are not the variable costs. They are only a part of the variable costs. And which part they are? So variable costs are P times X. Variable costs per unit. Great. So variable costs per unit. And this is actually only true because we have here a linear dependence. Because if I put it all only here with some other color, in general, we assume that we have increasing variable costs. So in general, we could think, or let's say, if we take another cost function is maybe alpha plus beta x squared. Then we could not interpret this as cost per unit, but this can be interpreted as costs per unit because we have a linear dependence. And if we have a linear dependence, then of course also variable costs per unit also coincide with the marginal costs. So this, because this is our assumption of our cost function, these are also marginal costs, because marginal costs are nothing else than the first derivative, and the first derivative of c of x is then just b. So calculate the correlation. So then we have C. We want to calculate R. Well, of course, we can then go into our other formula where we have it. This was here, I think. We just can take this formula, putting all our numbers in, or taking this dependence between B are and the variances of x and y, or we can also use this formula here for r squared, and then since we know that we have a positive dependence, we can calculate backwards the correlation coefficient. And I think from my table this is the fastest possibility to calculate it. So let's take this one, and where we are here, let me take it here. Because if we go in our table, then I can calculate y hat, and y hat is given by a plus b times x. And what do we need for r squared? The difference between the theoretical values y, oops, and the mean, and the total difference between the data points, and oh, this has to be this is not good that there is a y hat between the mean. So then we need y hat minus y bar squared, and this is then y hat minus y bar squared. This was 9,306 squared, and this has to be fixed. And we need also y minus y bar open y minus y bar fix it squared Then we need also the summation. Oh, this is wrong here. This were the sum. And then we have r squared equals this over this. Something is wrong here. What did I do? C4 minus y bar. This is all this is right. G over H16. Oh, I copied y hat. So this is always good. This was a good point that you know what you are doing if you are going into some software package. So I just copied because I thought, okay, here I'm always doing the summation. Then let's just copy this cell to the right. But at this cell, I did something wrong because I just calculated all this down here and then I came to this number. But at this point, I also have to copy this formula here, the summation to the right, and therefore I just, because I was too fast, copied the formula and not the summation. And now I'm at the right in business again. So I have 0.87 and then I have R as the root equals root of this, and it is plus the root since we know that B is positive. Oh, this has to be on the right that you see something. So here we are. No, not. Now you see the values. Or then let's just put these values here in. Again. So now you should see anything again. Oh, I'm 5 minutes over. Sorry. But we are almost done. Oh, yeah. So we have 87% is explaining of our regression. 0.87, and therefore we have R is roughly 0.93. Then let's just take the last one noch, estimation of 1,100 hectoliters. This, of course, is done by C of 1,100 equals 3,503.08 plus 5,865 times 1,000, and this is then C of equals A times plus B times 1,100 is 9,952.07.067. 9,952.067. Okay, then let's stop it.